Now in this lecture I will answer two questions. On both questions we'll find out the area of a shaded region. Let's start with the first question. In the drawing we have the big quarter circle AOB. Inside this big quarter circle we have a semicircle and this small quarter circle. Again, our task is to find out the size of this shaded area. We also know that AO equals to 10 units in its length. AO is the radius of this big quarter circle AOB, and it equals to 10, so the radius of this big quarter circle AOB equals to 10. Therefore, BO is also the radius of this big quarter circle AOB, is equals to 10. The next step, we define the center of this semicircle. This point is point C. BO is the radius of the big quarter circle, but BO is also the diameter of this semicircle. So the diameter of this semicircle, BO equals to 10, and therefore the radius must be equal to 10 over 2, that is 5. So the radius CB of this semicircle equals to 5 units in its length. The radius CO also equals to 5 units in its length. AOB is a quarter circle, and therefore this is a right angle. We define the touching point of this small quarter circle with this big quarter circle. This point is point P. We define this point Q, and we define this point as point S. This is the small quarter circle that touches externally this big semicircle at this point. So when we define their touching point, this point is point M. Repeat again that the small semicircles, and this is the small quarter circle that have an external arc with this semicircle at point M. So they touch each other externally at point M. And therefore we can implement here rule 10. We can click on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. So in the drawing we have those two circles that touch each other externally. This point P. The center of this circle is here at point O. The center of this circle is here at point M. The straight line that connects the centers, their centers together is of course the straight line OM. This straight line OM, according to this rule 10, must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, that is their touching point. Or OPM is one straight line. Again, OPM is one straight line. So if OPM is one straight line, it means that OM in total must be equal to OP plus PM. So we can implement rule 10 in our drawing. In our drawing, this is the small quarter circle that touch externally this big semicircle at point M. The center of this small quarter circle is at point Q. The center of this big semicircle is at point C. The straight line that connects the centers together is of course the straight line CQ. And according to rule 10, the straight line CQ must pass through point M, that is their touching point. Again, the straight line CQ must pass through point M, that is their touching point. So we'll join point C and Q together by a straight line, and the straight line CQ must pass through point M, that is their touching point according to rule 10. Then you can see that and the straight line CQ indeed passes from point M. That is the attaching point exactly like rule 10. So in the next step, I'll copy this right triangle COQ in the new equation. We will implement on it the Pythagoras theorem. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So, according to rule 10, QMC is one straight line, and therefore QC total must be equal to QM plus MC. So in total QC equals to QM. We define the radius of this QM is of course the radius of this small quarter circle, so we define the radius of this small quarter circle as x, therefore QM equals to x. Likewise, QP is also equals to x because it is the radius of the quarter circle. Point Q is the center of the quarter circle, point P is the point of the quarter circle itself, therefore QP is the radius of this quarter circle, that is equals to x according to our definition. So QC in total equals to QM, that is x, plus MC. MC is the radius of this semicircle, that is equals to 5. So in total QC equals to x plus 5. According to rule 10, QC in total equals to QM, that is x, plus MC, that is 5. So in total QC equals to x plus 5 units in its length. In the next step, we will join points O and P together by a straight line. But before that, we will implement the Pythagoras theorem on this right triangle, triangle COQ. We just write the formula that the hypotenuse CQ equals to x plus 5 units in its length. OQ is the missing side, so leave it as it is, and CO or OC is the radius of this semicircle, that is equals to 5. Okay, this is the right triangle CQO, that is the comment of the original drawing. In this right triangle CQO, according to the Pythagoras theorem, CQ squared, that is the square of the hypotenuse, equals to CO squared plus QO squared. So write it down. CQ squared, this is the square of the hypotenuse, is equal to CO squared plus QO squared. CQ is x plus 5, therefore CQ squared is x plus 5 squared. And it equals to CO squared. CO is 5, therefore CO squared is 5 squared, that is 25. Plus QO squared. QO is the missing side, so leave it as it is. So in total, according to equation 1, we found out that x plus 5 squared equals to 25 plus QO squared. Here we will subtract 25 from this equation, equation 1. And finally, we get that according to equation 1, q all squared equals to x plus 5 squared minus 25. In the next step, we will join points O and P together by straight line. Point O is the center of the biggest quarter circle. Point P is the point of the biggest quarter circle itself. Therefore, PO is the radius of this quarter circle. This is equals to 10 units in its length. PO equals to 10. PQ is the radius of this quarter circle. This is equals to x. So in the next step, I'll copy the right triangle P or Q in union touch, and we'll implement on it the Pythagoras theorem. So finally, this is the right triangle PQO, this is according to the original drawing. Here by PT is the measure for Pythagoras theorem. So in this right triangle PQO, according to the Pythagoras theorem, we get that PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. So it's long, and should not know that according to the Pythagoras theorem, in this right triangle PQO, PO squared, that is the square of the hypotenuse, is equal to PQ squared plus PO squared. PO is 10, therefore PO squared is 10 squared, that is 100. And it is equals to PQ squared. PQ is x, therefore PQ squared is x squared plus QO squared. QO is the missing side, so relate this it is. So in total, according to equation 2, if we found out that 100 equals to x squared plus QO squared. Here we will subtract x squared from this equation 2, and finally get that according to equation 2, QO squared equals to 100 minus x squared. So according to equation 1, QO squared equals to 100 minus x squared. Well, according to equation 1, again according to equation 2, QO squared equals to 100 minus x squared. When according to equation 1, we only found out that q all squared equals to x plus 5 squared minus 25. Therefore, we get the equation 3 that states that q all squared according to equation 1 must be equal to q all squared according to equation 2. And again, this is equation 3 that says that q all squared according to equation 1 must be equal to q all squared according to equation 2. Q all squared according to equation 1 equals to x plus 5 squared minus 25. Again, q all squared according to equation 1 equals to x plus 5 squared minus 25. And it must be equal to q all squared according to equation 2. Q all squared according to equation 2 equals to 100 minus x squared. So in total, according to equation 3, I should found out that x plus 5 squared minus 25 equals to 100 minus x squared. So here we open the brackets of this expression and get that according to equation 3, x plus 5 squared equals to x squared plus 5 squared, that is 25, plus 2 times x times 5, that is 10x. Here also minus 25. And this equals to 100 minus x squared. So in this question we have 25 minus 25, that is 0. After we get 25 from the equation 3, we left only with x squared plus 10x equals to 100 plus x squared. And again, according to equation 3, I should find out that 100 plus 10x is equal to 100 plus x squared. So here we add x squared to the equation 3. And so again, according to equation 3, x squared plus x squared is 2x squared plus 10x equals to 100. Here we subtract 100 from this equation 3 and get the 2x squared plus 10x minus 100 equals to 0. So we divide this equation 3 by 2. And finally again, according to equation 3, 2x squared over 2 is x squared. And we have 10x over 2 is 5 squared. And here we have minus 100 over 2 is minus 50 equals to 0 over 2 is 0. So in total, we should know that x squared plus 5x minus 50 equals to 0. This is a quadratic equation, And the general formula for a quadratic equation is as follows. Ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. And again, x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Now a specific quadratic equation, that is to say x squared plus 5x minus 50 equals to 0. The variable that we are looking for is x, and the coefficient a equals to 1, the coefficient b equals to 5, and the coefficient c equals to minus 50. All that is left to do here, the only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for x. In this way we get the value of x. X is the length, x is the radius of this small quarter circle. So here we have x equals to minus b. B is 5, so minus b is minus 5, plus minus square root of b squared. B is 5, so b squared is 5 squared, that is 25. Minus 4 times a times c. This is minus 4 times a is also minus 4 times 1 is minus 4 times c. Minus 4 times minus 50 is plus 200. Divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total we should found out that x equals to minus 5 plus minus, inside the root we have 225 over 2. And the square root of 225 is 15. So in total we found out that x equals to 5 plus minus 15 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to minus 5 minus 15 over 2. And again, the first solution for x is that x equals to minus 5 minus 15 is minus 20, and minus 20 over 2 is minus 10. So we got that x equals to a negative number. X is the radius of this small quarter circle, and therefore it must be a positive number. As you know, x is a length, and it's a length must be a positive number. Therefore, we consider the possibility that x equals to any negative number. S can never be equal to, understand that it's a negative number. And the second solution for x is that x equals to minus 5 plus 15 minus 5 plus 15 over 2. Minus 5 plus 15 is 10, and 10 over 2 is 5. So if you found out that x equals to 5 units in its length. The radius x of this one quarter circle is equal to 5 units in its length. The second, so we actually found out that x equals to 5. That is the second solution. X equals to 5 units in its length. The radius of the small quarter circle is equals to 5 units in its length. Our test is to find out the size of this shaded area. So what is the size of the shaded area? What is the size of the shaded region? The size of the shaded region must be equal to the area of the big quarter circle AOB. So it is equals to the area of the big quarter circle AOB. Minus the area of this semicircle minus the area of this small quarter circle PQS. So repeat again, in total we found out that the size of this shaded area, or the area of this shaded region, in total is equal to the area of the big quarter circle AOB minus the area of the semicircle minus the area of the small quarter circle minus the area of the small quarter circle PQS. So what is the area of this big quarter circle? Because of the fact that the radius of this big quarter circle equals to 10, and the area must be equal to pi times the radius squared over 2. So it is pi times 10 squared over 2. Now the big quarter circle equals to pi times the radius squared, that is 10 squared over 2. Minus the area of this semicircle. The radius of this semicircle is 5, and therefore the area must be equal to pi times 5 squared over 2. Minus the area of this small quarter circle PQS. The radius of this small quarter circle x equals to 5, and therefore the area of this small quarter circle must be equal to pi times 5 squared over 4. So now the big quarter second AOB equals to pi times 10 square over 4. 10 square is 100. So in total, this expression equals to 100 pi over 4. Minus, we have 5 square times pi over 2. 5 square is 25, so it is 25 pi over 2. So we multiply both the numerator and the denominator of this expression by 2, and we get that 25 pi times 2 is 50 pi, so it is minus 50 pi, and 2 times 2 is 4. So in total this expression is equal to minus 50 pi over 4. Here we have 5 square, 25, so in total in the numerator we have 25 pi over 4. So here we take 4 as a second factor out of those three expressions, and you get that 100 pi minus 50 pi is 50 pi, and 50 pi minus 25 pi is 25 pi. So in total we should know that there of this shaded region is equal to either 25 pi over 4 square units in size, or in terms of numbers it is equal to 19.635 square units in size. Okay, again, I should know that the area that we are looking for in this question, that is, there are this shaded region. In total, it is equal to either 25 pi over 4 square units in size, or in terms of numbers, it is equal to 19.635 square units in size. So we finished to answer the first question. In the next step, I present you the second question, and we'll solve the second question of this lecture. In the second question, our task is to find out the area of this shaded region. So, you know that those two semicircles converge to each other. That is to say, they are identical, and therefore they have also the same areas. We also know that AB, the diameter of this semicircle, equals to 5 units in its length. When we find the center of this semicircle, this point is point O. And because of the fact that the diameter of semicircle AB is 5, the radius must be equal to 5 over 2. So the radius AO is 5 over 2, and the radius OB is also 5 halves. In the next step, we will divide this drawing, the drawing of this question, into 3 parts. The first part will be the shaded area, and we'll define the size of this shaded area as C. That is to say, the size of this shaded area is equal to C square units in its size. Okay? This shaded area is equal to C is correct in its size. Likewise, we define the intersection point between the diameter CB and this semicircle. This point is point M, and we define the size of this small semicircle MB SB. That is to say, the size of this area is equal to B square units according to our definition. And finally, we define the size of this shape AMB as SA. And again, this shape AMB is equal to A square root in its size according to our definition. And because of the fact that those two circles can go into each other, they must have also the same areas. That is to say, the area of this semicircle AB must be equal to the area of this semicircle CB. So I write it down. The size of this shaded area and the size of this semicircle AB, or the area of this semicircle AB, is equal to the area of this semicircle CB. I repeat again, according to equation 1 and according to what is given in the question, the area of semicircle AB equals to the area of semicircle CB because they can go into each other. What is the area of the semicircle AB? Semicircle AB consists of those two smaller parts, those two smaller shapes, and therefore the area of semicircle AB must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal in total to A plus B. In conclusion, we found out that the area of this semicircle AB equals to A plus B square root in size. And it is equals to the area of semicircle AB equals to the area of semicircle CB. What is the area of the semicircle CB? Actually, it is very easy to see that semicircle CB consists of those two shapes, and therefore the area of semicircle CB must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to B plus C. The area of semicircle CB equals in total to B plus C square root in size. So according to equation 1, we found out that A plus B equals to B plus C. So here we will subtract B from this expression, equation 1. And finally get that according to equation 1, here B will get cancelled. And we left only with A is equals to C. That is to say, this is shape A and B that is equals to A square root inside, and it is equals to this shape that is the shaded area. that equals to 6 coincident sides. So those two areas are equal to each other in their sizes. So in order to find out the size of this shaded area, we just have to find out the size of this shape A and B. Why? Because A equals to C. So the shaded area, the size of this shaded area is equal to the area of this shape A and B. So just have to find out the size of this shape A and B, and it will be equal to the size of this shaded area C, because C equals to A. Okay, so in the next step we will do a construction, that is to say from point M, from this point M, we will draw perpendicular on AB. And again from point M, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. When we find the touching point of the perpendicular from point M and AB, this point is point Z. When we find the length of line at MZ, or the length of this perpendicular MZ as H. Likewise, we join points A and M together by a straight line. By joining points A and M, we get the deal peripheral angle A and B. This is peripheral angle A and B. Peripheral angle A and B subtend on AB, that is the diameter of this semicircle. Therefore, according to rule 7, any peripheral angle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Repeat quickly on rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle or semicircle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. This is peripheral angle ACB that subtend on chord AB, that is the diameter of this circle, and therefore according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size. Repeat again that according to rule 7, any peripheral angle that subtend on the diameter of a circle or a semicircle must be equal to 90 degrees in its size. So as I mentioned before, we can definitely implement rule 7 in our drawing. Why? Because in our drawing, we have peripheral angle A and B that subtend on AB, that is the diameter of this semicircle, and therefore it must be equal to 90 degrees in its size according to rule 7. So peripheral angle A and B is a right angle. In the next step, we will join points O and M together by straight line. Point O is the center of this semicircle, and point M is a point on the semicircle itself. So by doing this construction, we created center angle AOM. This is center angle AOM. But what is the size of this center angle AOM? Center angle AOM subtend on chord AM. Again, center angle AOM subtend on this chord called AM. Likewise, we have peripheral angle ABC. This is peripheral angle ABM. This is peripheral angle ABM. That subtend on the same chord called AM. And because of the fact that those two angles they are both subtend on the same chord called AM, the size of this center angle AOM must be twice as large as the size of this peripheral angle ABM that is subtend on the same chord called AM. And because of the fact that the size of this peripheral angle ABM is equal to 15 degrees, therefore the size of this center angle AOM that subtend on the same chord called AM must be equal to 15 degrees times 2, that is 30 degrees. So if you know, according to Rule 13, of course. So I'll repeat quickly on Rule 13. According to Rule 13 states that a center angle is twice as large as the peripheral angle that's subtended on the same chord. So in the drawing we have a circle. This is peripheral angle ACB that's subtended on chord AB, and it is equal to theta degrees in its size. Likewise, we have center angle AOB subtended on the same chord AB, and according to this Rule 13, the size of this center angle AOB must be twice as large as the size of this peripheral angle ACB, because they are both subtended on the same chord AB. But the size of this peripheral angle ACB is theta, and therefore the size of this center angle AOB that's subtended on the same chord AB must be equal to 2 theta. We already implemented Rule 13 in our drawing. So as I mentioned before, those two angles, they are both subtended on the same chord AM. And the size of this center angle AOB must be twice as large as the size of this peripheral angle ABMBA that's subtended on the same chord AM. The size of this peripheral angle ABM is 15 degrees, and therefore the size of this center angle AEOM that's subtended on the same chord AM must be equal to 15 degrees times 2, that is 30 degrees. What is the definition of this shape AOM? Shape AOM that includes also RKM. Again, shape AOM includes RKM also. This is like a slice of a pizza. It is a sector. So what is the definition of a sector? A sector is a portion of a circle. The green shape AOB is a sector. It is a portion of this circle enclosed by 2 radii and RKB between them. Again, a sector is a portion of this circle. It is enclosed by those 2 radii and RKB between them. The 2 radii are defined also as the legs of the sector. What is the area of this green sector AOB? The area of sector AB equals to the area of the circle that contains the sector, that is to say pi r squared times the angle between the legs of the sector, that is theta, over 360 degrees. Repeat again, the area of this sector AOB equals to pi r squared times theta over 360 degrees. Okay. We already found out that the size of the shaded area is exactly like the size of this shape AMB, because A equals to C. So we just have to find out the size of this shape AMB. It will be equal to the size of this shaded area, that is the area that we are looking for in this question, because A equals to C. So we just have to find out the size of this shape AMB. This shape AMB consists two smaller shapes. It consists of this sector AOM, and it also consists of this triangle MOB. And therefore, in total, the size of this shape AMB, it is equal to the sum of those two smaller shapes that it consists of. That is to say, it must be equal to the area of this sector AOM plus the area of this triangle MOB. So, already known, we found out that the size of this shaded area is equal to the size of this shape AMB. And the size of this shape AMB consists of two smaller shapes. The first shape, that this big shape and B consists of is sector AOM. So it is the area of the first shape, that is the area of this sector AOM. The rounded line above AOM is a sign for a sector. It means sector or AOM. Oh, total means the area of sector AOM. So it is the area of the first smaller shape that A and B consists of, plus the area of this second shape that A and B consist of. The second shape is it is actually the triangle MOB. So I repeat again that you know that those two shapes are equal to each other in their sizes. That is to say, the size of this shaded region is equal to the size of this shape A and B. So therefore, we just have to find out the size of this shape A and B, and this will be equal to the size of this shaded area, because A equals to C. The shape A and B consists of two smaller shapes. It consists of this sector AOM and also this triangle MOB. And therefore, in total, the size of this shape A and B must be equal to the area of the first shape that it consists of, that is actually sector AOM, plus the area of the second shape that it consists of, that is actually triangle MOB. So in total, the size of the shaded area equals to the area of sector AOM plus the area of triangle MOB. That is the two shapes that this A and B consists of. Okay, repeat again that A equals to C, and therefore the shaded area equals to A and B. Okay, so what is the area of the first shape that A and B consist of? It is the area of sector AOM. We only found out that the area of any sector equals to pi r squared. It is the area of the semicircle that contains the sector. It is pi r squared. It is related to the circle, of course. The area of the circle that consists of this sector MOA. The area of the circle equals to pi r squared. R is the radius of the circle that contains this sector AOM. So it is pi r squared times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. Plus the area of the second shape that A and B consists of. The second shape it is triangle MOB. What is the area of this triangle MOB? It is equal to the base OB. OB is the radius of the semicircle, times the height of the base. The height must create 90 degrees with the base OB. And indeed, MZ creates 90 degrees with the base OB. If you extend OB, you create 90 degrees with the base. MZ creates 90 degrees with the extended BO. And therefore, the height is MZ and this is equals to H. So the height is H over 2. The area of the triangle equals to the base OB times the height to the base H over 2. So in total, the size of the shaded area equals to pi r squared times 30 degrees over 360 degrees times the area of the circle, triangle MOB, that is actually the base OB times the height H over 2. R is 5 halves. R is the radius of this semicircle, that is 5 halves. And therefore r squared is 5 halves squared. So in total, pi r squared equals to pi times 5 halves squared times 30 degrees over 360 degrees. And we have here OB times H over 2. OB is 5 halves. It is the radius of the semicircle times the height H. We already found out that the height H So we have to find out the value of h. So I write it down. It is equals to h, limit as it is, OB is 5 ups times the height edge over 2. You just have to find out the height edge of this triangle MOB. In order to find out the height edge of this triangle MOB, you just focus on this right triangle, on this triangle ACB. So copy the right triangle ACB, and in the page you analyze this triangle ACB. Actually, the only missing variable is the right edge. We find out the right edge, and this way we find out the size of the shaded area, because R is 5 Rs, and the only missing variable is the right edge of this triangle MBO. So copy the right triangle A and B. In the new page, it is not the right triangle, and copy triangle A and B. In the new page, we will analyze triangle A and B in order to find out the right edge of this triangle MOB. So actually, this is triangle A and B that are going from the original drawing. In the next step, we'll calculate the area of this triangle A and B in two different methods. And then we'll create an equation that says that the area of triangle A and B, this triangle A and B, according to the first calculation, must be equal to the area of triangle A and B, this triangle A and B, according to the second method of calculation. So the area of this triangle A and B, according to the first method of calculation, will be equal to the base AB times the height edge over 2. In the next step, this is of course a right angle. It is very, very important. According to Rule 7, this is a right angle. Angle A and B is a right angle. Angle A and B is a right angle because it's obtained on the diameter AB of this semicircle. According to the second method of calculation, the area of this triangle A and B will be equal to the base AM times the height MB over 2. And again, this is equation 1 that says that the area of this triangle A and B according to the first method of calculation must be equal to the area of this right triangle A and B according to the second method of calculation. It is given us the equation that AB equals to 5. So here we substitute AB by 5. And get according to equation 1, 5 h over 2 equals to AM times MB over 2. So here we have 2 on both sides of the equation, so 2 will get cancelled. After we cancel 2, we left only with this equation 1 that states that 5h equals to AM times MB. And again, according to this equation 1, 5H equals to AM times MB. Now we have to find out the value of AM and MB. So copy this target AB again here, and we continue to analyze this line. Target AB. This is angle AB, and that equals to 15 degrees in size according to what is given as the question. So in this right line A and B, sinus 15 degrees equals to AM over AB. AB is 5. So sinus 15 degrees equals to AM. AM is the missing side, so this is it is, over AB. AB is 5. So sinus 15 degrees equals to AM over 5. Here we will multiply this equation by 5. And finally we get that AM equals to 5 times sinus 15 degrees. And again, if you found out that AM equals to 5 times sinus 15 degrees. What is the value of cosine 15 degrees? Cosine 15 degrees is equal to MB over AB. And again, this right triangle AMB, cosine 15 degrees equals to MB over AB. Here we multiply this equation by AB, and finally we get that MB equals to MB equals to AB times cosine 15 degrees. AB is 5, therefore MB in total equals to 5 times cosine 15 degrees. In conclusion, we found out that MB equals to 5 times cosine 15 degrees, and AM equals to 5 times sinus 15 degrees. According to equation 1, 5H equals to AM times MB. So I did not. H equals to AM times MB. So now we can substitute this equation 1 AM by 5 times sinus 15 degrees and MB by 5 times cosine 15 degrees. We'll do it now. We get that according to equation 1, 5H equals to, again, AM is 5 times sinus 15 degrees times MB. MB is 5 times cosine 15 degrees. So in total we should find out that 5H equals to 5 times sinus 15 degrees times 5 times cosine 15 degrees. So here we will divide this equation 1 by 5. And finally get that according to equation 1, here 5H over 5 is H, is equal to, here we have 5 times 5, so 1 5 will get cancelled and we'll have only with 1 5. So in total, in this side of the equation, we have 5 times sinus 15 degrees times cosine 15 degrees. So in total, according to equation 1, we have found out that h, the value that we are looking for, the value of this mz is equal to h. In total, it is equal to 5 times sinus 15 degrees times cosine 15 degrees. Here we use the geometric identity that states that sinus 2a equals to 2 sinus a cosine a. So according to this geometric identity, I will divide this geometric identity by 2, and finally get that sinus 2a over 2 is equal to sinus a times cosine a. We use this geometric identity in order to find out the value of sinus 15 degrees times cosine 15 degrees. So according to equation 1, h equals to 5 times sinus 15 degrees times cosine 15 degrees. But we have the geometric identity that states that sinus a times cosine a equals to sinus 2a over 2. And according to this geometric identity, we get that sinus 15 degrees times cosine 15 degrees will be equal to sinus 2 times 15 degrees, that is 30 degrees, over 2. And again, sinus 15 degrees times cosine 15 degrees, according to this geometric identity, will be equal to sinus 2 times 15 degrees, that is 30 degrees, over 2. And we have here 5 equals to h. So in total, we have found out that h equals to 5 times sinus 30 degrees over 2. So h equals to 5 over 2, sinus 30 degrees is 1/2. So in total, we have found out that h equals to 5 over 2 times 2, that is 4. So h equals to 5 quarters. H equals to 5 quarters. We already found out that the shaded area in total equals to pi times 5 half squared times 30 degrees over 360 degrees plus 5 over 2 times h over 2. We just right now found out that h equals to 5 quarters. So we substitute h by 5 quarters and we get that here we have 5 over 2, h equals to 5 quarters, divided by 2. So in total this expression equals to 5 times 5 over 2 times 4 times 2. Here we have 5 half squared is 5 squared is 25 over 2 squared that is 4. So in total in the numerator we have 25 pi over 4. Here we have 30 degrees over 360 degrees is 1 over 12. So in total we found out that the shaded area equals to 25 pi over 4 times 12 plus 5 times 5 over 2 times 4 times 2. So total it is equals to 25 pi over 4 times 12 is 48 plus 5 times 5 is 25 over 2 times 2 is 4 and 4 times 4 is 16. So in total we should find out that the size of the shaded area is equals to 25 pi over 48 plus 25 over 16 square units in size. Or in terms of numbers, it is equal to 3.2 square units in size. And again, we should find out that the area that we are looking for this question, this shaded region is equal to 3.2 square units in its size. So we finished to answer on the second question. In the next step, I will start the lecture. We'll start with the first question, of course. The first question, actually in both questions, our test is to find out the area of the shaded region. In this question, we have to find out the area of this shaded region. So in the drawing, we have the big quarter circle AOB. Inside this big quarter circle AOB, we have this small semicircle and this small quarter circle. We also know that AO, that is the radius of this big quarter circle AOB, equals to 10 units in its length. Again, our task is to find out the size of this shaded region. So first of all, the radius of this big quarter circle AOB equals to 10. So AO is the radius that is equals to 10. OB is also the radius of this big quarter circle, and therefore it is equals to 10. BO is also the diameter of this semicircle. If the diameter of this semicircle equals to 10, the radius must be equal to 5. So the radius CB equals to 5, the radius CO of this semicircle also equals to 5 units in its length. In the next step, we define the touching point between this semicircle and this small quarter circle. This point is point M. Those two shapes, that is to say the semicircle, touch externally this small quarter circle at point M. And therefore we can implement here rule 10. We can click on rule 10. If two circles touch each other externally, then the straight line that connects the centers together passes for their touching point. So the drawing, we have those two circles that touch each other externally, this point P. The center of this circle is there at point O. The center of this circle is there at point M. The straight line that connects the centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through point P, that is the touching point. Again, the straight line OM must pass through point P, that is the touching point. Or OPM is one straight line. Again, OPM is one straight line. And if OPM is one straight line, it means that OM in total must be equal to OP plus PM. So can actually implement rule 10 in our drawing. In our drawing, the small quarter circle touches externally this big semicircle at point M. The center of this small quarter circle is here at point Q. The center of this big semicircle is here at point C. The straight line that connects the centers together is of course the straight line CQ. And according to this to rule 10, the straight line CQ must pass through point M, that is the touching point of CMQ is one straight line. If CMQ is one straight line, it means that CQ in total must be equal to CM plus MQ. So CQ in total equals to CM. CM is the radius of this semicircle, that is 5, plus MQ. We define the radius of this semicircle as x. We define the radius of this small quarter circle as x. And therefore QM is the radius of this small quarter circle, that equals to x. So in total CQ equals to CM, that is 5, plus MQ, that is x. So in total CQ equals to x plus 5 units in its length. In the next step, I covered the right triangle COQ in a new page and implemented on this right triangle the Pythagoras theorem. AOB is a quarter circle, and therefore this is a right angle. Likewise, PQS is also a quarter circle, and therefore this is a right angle. So in the next step, we implemented the Pythagoras theorem on this right triangle CQO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually this is the right triangle CQO, that is according to the original drawing. This right triangle CQO, CQ squared, that is the square of the hypotenuse, equals to CO squared plus OQ squared. So CQ is x plus 5, therefore CQ squared is x plus 5 squared, and it is equals to CO squared. CO is 5, therefore CO squared is 5 squared, that is 25. Plus QO squared. QO squared is the missing side, so believe it as it is. So in total, according to equation 1, we have found out that x plus 5 squared equals to 25 plus QO squared. Here we subtracted 25 from this equation 1. We found out that according to equation 1, QO squared equals to x plus 5 squared minus 25. In the next step, we join points P and O together by a straight line. Point O is the center of this big quarter circle. Point P is a point of the big quarter circle itself. Therefore, OP is the radius of this big quarter circle, that is equals to 10 units in its length, according to what is given as the question. So in the next step, I copied the right triangle POQ in a new page and implemented on this right triangle POQ the Pythagoras theorem. PQ or QP is of course the radius of this small quarter circle, that is equals to x according to our definition. Actually, this is the right triangle POQ, that is according to the original drawing. In this right triangle POQ, PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. PO is 10, therefore PO squared is 10 squared, that is 100, and it is equals to PQ squared. PQ is x, therefore PQ squared is x squared plus QO squared. So here we subtracted x squared from this equation 2, and found out that according to this equation 2, QO squared equals to 100 minus x squared. This is according to equation 2. When according to equation 1, we only found out that QO squared equals to x plus 5 squared minus 25. So we have two different equations for QO squared. Therefore, we created equation 3 that states that QO squared according to equation 1 must be equal to QO squared according to equation 2. QO squared according to equation 1 equals to x plus 5 minus 25, and it must be equal to QO squared according to equation 2. QO squared according to equation 2 equals to 100 minus x squared. So in total, according to equation 3, I should found out that x plus 5 squared minus 25 equals to 100 minus x squared. We open the brackets of this expression, and we found out that x plus 5 squared equals to x squared plus 5 squared, that is 25, plus 2 times x times 5, that is 10x, minus 25, and it is equals to 100 minus x squared. This is the equation 3, we have 25 minus 25 is 0. After we cancel 25, we have only with x squared plus 10x, that is equals to 100 minus x squared. Again, according to equation 3, we found out that x squared plus 10x equals to 100 minus x squared. We added x squared to this equation 3, found out that according to this equation 3, x squared plus x squared is 2x squared plus 10x equals to 100. Here we subtract 100 from this equation 3, and found out that according to this equation 3, 2x squared plus 10x minus 100 equals to 0. Here we divided this equation 3 by 2, and finally found out that 2x squared over 2 is x squared, plus 10x over 2 is 5x, minus 100 over 2 is minus 50, it is equals to 0 over 2. 0 over 2 is 0. So in total we shall find out that x squared plus 5x, x squared plus 5x minus 50 equals to 0. So actually, this is a quadratic equation. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus 4 to b squared minus 4 times a times c over 2a. In our specific quadratic equation, x, that is to say x squared plus 5x minus 50 equals to 0, the variable that we are looking for is of course x. The coefficient a equals to 1, the coefficient b equals to 5, and the coefficient c equals to minus 50. So the only thing that is left to do is to put this data of our specific quadratic equation inside this general formula for x, and this way we find out the value of the values of x. X is the radius of this small quarter circle. So we did it. We found out that x equals to minus b. B is 5, so minus b is minus 5, plus minus square root of b squared. B is 5, so b squared is 5 squared, that is 25. Minus 4 times a times c. So this is minus 4 times a is 1, so minus 4 times 1 is minus 4 times c. Minus 4 times c is minus 4 times minus 50. Minus 4 times minus 50 is 200. So total minus 4 times a times c is plus 200. So inside the root we have 25 plus 200 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total we should find out that x equals to minus 5 plus minus 25 plus 200 over 2. 25 plus 200 is 225. So in total we should find out that x equals to minus 5 plus minus 200, square root of 225 over 2. The square root of 225 is 15. So in total we should find out that x equals to minus 5 plus minus 15 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to minus 5 minus 15 over 2. Minus 5 minus 15 is minus 20, is minus 20 over 2 is minus 10. So according to the first solution, x equals to minus 10. Because of the fact that x is the length of this radius of this small quarter circle, x as a length, x as a length, it must be a positive number. Minus 10 is a negative number, therefore this solution is incorrect solution. So we will take into account only the second solution for x. And the second solution for x is that x equals to minus 5 plus 15 over 2. Minus 5 plus 15 is 10, and 10 over 2 is 5. So the second solution for x is that x equals to 5. That is to say, the length of this radius of this small quarter circle is equal to 5 units. Our task is to find out the size of this shaded area. So what is the size of this shaded region? From the drawing, it is very easy to see that the size of this shaded region in total must be equal to the area of this big quarter circle A or B minus the area of this semicircle minus the area of this small quarter circle PQS. Repeat again, the size of this shaded region in total it must be equal to the area of the big quarter circle A or B minus the area of the semicircle minus the area of the small quarter circle PQS. What is the area of this big quarter circle A or B? Because of the fact that the radius of this big quarter circle is 10, the area must be equal to pi r square over 2. That is to say, pi times 10 square over 2. So in total, the area of the big quarter circle must be equal to pi times 10 square over 4, of course. So it is a quarter circle, therefore we have to divide it by 4. Minus the area of this semicircle. The radius of this semicircle is 5, and therefore the area must be equal to pi r square over 2. That is to say, pi 5 square over 2. The semicircle is pi 5 square over 2, so it is minus pi 5 square over 2. Minus the area of this small quarter circle PQS. The radius of this small quarter circle PQS is x, that equals to 5. And therefore the area of this small quarter circle PQS must be equal to pi times 5 square over 4. So total area of the quarter circle PQS must be equal to pi times 5 squared over 4. So here we have 10 squared is 100. So in total, in the numerator we have 100 pi over 4. Here we have 5 squared is 25. So in total, in the numerator we have 25 pi over 2. So we multiply both the numerator and the numerator by 2 in order to become a factor of the other two expressions. 25 pi times 2 is 50, and 2 times 2 is 4. We multiply it by 4 and then we divide it by 4, so we change nothing. Here we have 25 pi over 4. 5 squared is 25. So in total it is in the numerator of 25 pi over 4. Here we took 4 as a common factor out of these three expressions. And in total we found out that 100 pi minus 50 pi is 50 pi, and 50 pi minus 25 pi is 25 pi. So in total this expression equals to 25 pi over 4. So if you found out that the area that we are looking for this question, that is the size of this shaded region, in total it is equal to either 25 pi over 4 square inches in size, or in terms of numbers, it is equal to 19.635 square inches in size. So we finished to repeat on the first solution. In the next step, repeat on the second solution of the second question. Our task in the second question is to find out the size of this shaded region, or the area of this shaded region. So in the drawing we have those two semicircles that intersect with each other at those 2 points. We know that the diameter AB of this semicircle equals to 5, and therefore the radius OB is 5 over 2. The radius OA is also 5 over 2. We know that those two semicircles can go into each other, and therefore they must have also the same areas. That is to say, the area of this semicircle AB must be equal to the area of this semicircle CB. And again, because of the fact that those two semicircles can go into each other, they must have also the same areas. That is to say, the area of semicircle AB must be equal to the area of semicircle CB. We divided the total area of this drawing into 3 parts. The first part is the shaded area. We define the size of this shaded area, that is the area that we are looking for this question, as C. That is to say, it is equal to C square units in its size according to our definition. Likewise, we define the second part, that is this shape MB, as B. That is to say, it is equal to B square units in its size according to our definition. And finally, the third part is this shape A and B. Shape A and B consists of this arc AM. So the third part is this shape A and B. We define the size of this third part A and B as A. That is to say, it is equal to A square units in size according to our definition. So what is the area of this semicircle AB? Semicircle AB is divided into 2 parts. It consists of those 2 shapes. And therefore, the area of this semicircle must be equal to the sum of the areas of those 2 shapes that it consists of. That is to say, it must be equal to the area of this first shape, that is equal to A square units in size, plus the area of this second shape that it consists of, that is actually it is equal to B square units in size. So in total, the area of this semicircle AB must be equal to the sum of the areas of those 2 shapes that it consists of. That is to say, it must be equal to A plus B. Therefore, we should find out that the area of semicircle AB equals to A plus B. What is the size of this semicircle CB. Semicircle CB consists of those two shapes. And therefore, the area of semicircle CB must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to B plus C. And we found out that the area of semicircle CB equals to B plus C. So in total, according to equation 1, we found out that A plus B equals to B plus C. Here we subtract the B from this equation, and finally found out that A equals to C. So those two areas, they are equal to each other. That is to say, the size of this shaded region is equal to the size of this shape ACB. So we just have to find out the size of this shaded region ACB. This will be equal to the shaded area, that is the area that we are looking for this question, because A equals to C. And this shape AMB consists of two smaller shapes. It consists of this sector AOM, and it consists of this triangle MOB. And therefore, the area of this shape AMB must be equal to the sum of the areas of those two shapes that it consists of. But before that, we actually join points O and M together by straight line. We join points A and M together by straight line. By joining points A and M, we created triangle A and B. Triangle A and B subtend on A and B, that is the diameter of this semicircle, and therefore it is equal to 90 degrees in size. By joining points O and M, we created side triangle AOM. Side triangle AOM subtend on chord AM. Likewise, we have triangle ABC that subtend triangle ABM that subtend on the same chord called AM. And because of the fact that those two angles are both subtend on the same chord called AM, the size of this triangle AOM must be twice as large as the size of this triangle ABC. Why ABM? Why? Because they are both subtend on the same chord called AM. But the size of this triangle ABM is 15. Therefore, the size of this triangle AOM that subtend on the same chord called AM must be equal to 15 degrees times 2, that is 30 degrees. So this is shape AOM. Shape AOM, it looks like a slice of a pizza. What is it is defined as a sector. A sector is a portion of a circle enclosed by two radii and arc AM between them. The green shape AOB is a sector. You can see that it is like a slice of a pizza. It consists of two radii, it is enclosed by two radii and arc AB between them. And the area of this sector AOB must be equal to the area of the circle that contains the sector, that is pi r squared, times the angle between the legs of the sector, that is theta over 360 degrees. Repeat again, the area of the sector AOB in total, it is equal to pi r squared times theta over 360 degrees. So as I mentioned before, those two shapes are equal to each other in their sizes. So in order to find out the size of this shaded region, we just have to find out the size of this shape A and B, because they are equal to each other in their sizes. This is shape A and B that consists of those two smaller shapes. The first shape that it consists of, it is sector AOM. And the second shape that it consists of, it is this triangle AMOB. So the sum of the areas of those two shapes must be equal to the big shape A and B, because it consists of those two smaller shapes. So to that, we should found out that the shaded area is equal to the area of this shape A and B. And the area of this shape A and B, it consists of those two smaller shapes. The first shape that it consists of is sector AOM. plus the second shape that this consists of, that is triangle MOB. Therefore, in total, the area of the shaded region is equals to the area of this shape A and B. This shape A and B consists of this sector AOM plus this triangle MOB. And therefore, in total, the area of the shaded region or the shaded area equals to the area of the first shape that it consists of, that is actually the area of sector AOM plus the area of the second shape that it consists of, that is actually the area of triangle MOB. Repeat again that those two areas are equal to each other in their sizes. So in order to find out the size of this shaded area, we just have to find out the size of this shape A and B. But this shape A and B consists of those two smaller shapes. And therefore, in total, the size of this shape A and B must be equal to the area of the first shape that it consists of, that is actually the area of this sector AOM, plus the area of the second shape that it consists of, that is actually the area of this triangle MOB. Okay. So in total, the area of this shape A and B is equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to the area of the first shape that it consists of, that is actually sector AOM, plus the area of the second shape that it consists of, that is actually triangle MOB. What is the area of this sector AOM? According to the formula that I presented to you, the area of this sector AOM must be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector to 30 degrees over 360 degrees. Okay, again, in total, the area of sector AOM equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector that is 30 degrees over 360 degrees. And we have to add the area of this triangle MOB. The area of this triangle MOB equals to the base BO times the I to the base H over 2. So it is the base OB times the I to the base that is H over 2. OB is the radius of this semicircle, that is 5/2 times H, as H is 5/4. So before, we already found out that H equals to 5/4. So it is OB is 5/2 times H over 2. So I will just repeat on how we found out that H equals to 5/4. Actually, I copied, we joined points A and M together by straight line, we joined points O and M together by straight line. And from point M, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We defined SM, MZ as H. H is the number that we are looking for. So here, by joining points A and M, we can add triangle A and B. Triangle A and B subset on chord AB, that is the diameter of this semicircle, and therefore it must be equal to 90 degrees in size. So angle A and B equals to 90 degrees in size because it's subset on the diameter AB of this semicircle. So in the next step, I copy the triangle A and B in a new page and analyze this triangle A and B. This is the triangle A and B that I comment from the original drawing. This triangle A and B. The area of this triangle A and B equals to the base AB times the I to the base H over 2. This is according to the first method. In the next step, we calculated the area of this triangle A and B in a different way. The area of this triangle A and B equals to the base AM times the I to the base MB over 2. And the area of triangle A and B according to the first method must be equal to the area of triangle A and B according to the second method of calculation. That is to say, AB times H over 2 equals to AM times MB over 2. So here we have 2 on both sides of this equation, so 2 will get cancelled. AB equals to 5, so that AB by 5. So in total, we found out that 5H equals to AM times MB. In the next step, I copied the right triangle A and B here. We continue to analyze this right triangle A and B. According to what is given in the equation, angle MBA equals to 15 degrees. So in this angle MBA, sinus 15 degrees equals to AM over AB. AB is 5, so in total sinus 15 degrees equals to AM over 5. Here we multiply this equation by 5, and finally found out that AM equals to 5 times sinus 15 degrees. Cosine 15 degrees equals to MB over AB. Cosine 15 degrees equals to MB over AB. So it is AB is 5, so multiply this equation by 5 and found out that again MB equals to AB times cosine 15 degrees. AB is 5, so in total MB equals to 5 times cosine 15 degrees, while AM equals to 5 times sinus 15 degrees. According to equation 1, 5H equals to AM times MB, so we can substitute AM by 5 times sinus 15 degrees, and we can substitute MB in this equation by 5 times cosine 15 degrees. We did it, and we found out that in total, according to equation 1, 5H equals to 5 times sinus 15 degrees times 5 times 5 times cosine 15 degrees. So here we divided this equation 1 by 5, and we found out that according to equation 1, 5H over 5 is H, and here we have 5 times 5, so 1 5 we cancel, we left only with 1 5. So in total we found out that according to equation 1, H equals to 5 times sinus 15 degrees times cosine 15 degrees. Here we use the geometric identity that says that sinus 2A equals to 2 sine A cosine A. We divided this geometric identity by 2, and finally found out that sinus 2A over 2 equals to sinus A times cosine A. So according to equation 1, we already found out that H equals to 5 times sinus 15 degrees times cosine 15 degrees. And according to the geometric identity, that says that sinus A cosine A equals to sinus 2A over 2. And therefore, sinus 15 degrees times cosine 15 degrees will be equal to sinus 2 times 15 degrees, that is 30 degrees over 2. Therefore, this expression in total equals to 5 times sinus 30 degrees over 2. So it is H equals to 5 over 2, and sinus 30 degrees is 1 half. So in total, H equals to 5 over 2 times 2, that is 4. So in total, H equals to 5 quarters. This is inside H, this is equals to 5 quarters. So here we have H, and just I now found out that H equals to 5 quarters. So we substitute H by 5 quarters, H equals to 5 quarters, and we have to divide it by 2. Here we have 5 quarters squared is 25 over 4. So in total, in the numerator we have 25 pi over 4, and 30 degrees over 360 degrees is 1 over 12. So in total, this expression equals to 25 pi over 2 times 12, over 4 times 12, plus 5 times 5 over 2 times 4 times 2. So here we have 25 pi over 4 times 12, that is 48. So it is 25 pi over 48. Here we have 5 times 5 is 25, and 2 times 2 is 4, and 4 times 4 is 16. So in total, this expression equals to 25 over 16. So in total, the area of this shaded region is equals to either 25 pi over 48 plus 25 over 16 square inches in size, or in terms of numbers, the area of this shaded region in total is equals to 3.2 square inches in its size. Okay, thank you very much.